Hey, it's Mr. K. Let's talk a bit more about calorimetry with a bit more of a focus on labs this time. So we'll go back to Q equals mc delta T. Q is energy transferred, M is mass, C is specific heat capacity, and change in temperature is represented by delta T. So what does this actually mean in the lab standpoint? Let's take a look. So I like to use these energy bar charts or LOL charts to show the change of energy. So first thing we're going to talk about here is an exothermic reaction. Now, in an exothermic reaction, you may have heard or thought of it as energy leaving the reaction. So that's exactly the same way as we're going to think about it. Now, what's going to happen here in what we call a calorimeter, or in other words, a measure of energy, calories being energy and meter being measured, we're going to see how the calorimeter reacts to this energy being released. And because all that energy is being given off, the surroundings are going to go up in thermal energy. So I'm going to show that just with some qualitative bars here. Okay, I went from 1, I gained 3. Here's my 4 bars of thermal energy. Now, in terms of what that comes from, for the reaction isn't changing temperature itself. Instead, we're losing chemical energy. So we would have started high with, let's say, 4 bars, transferring away 3 bars, and ending up with 1 bar left of chemical energy. So then we have 2 different perspectives here that we'll talk about more as we go, but here comes the first time. In the eyes of the reaction, this is negative. But in terms of the calorimeter, it's going to experience a positive or a gain of energy. So a loss and a gain. No energy is being created or destroyed, only transferred. So because this reaction is losing energy, we're going to consider this an exothermic. Other terms you should be aware of as we go on. This chemical energy can also be called potential in terms of the potential energy stored in bonds. And this thermal energy is what's going to be called kinetic, as in the motion of particles. The faster the particles, the higher the temperature. Okay, let's look at a few examples. So this is data taken from a lab that we're looking at with hydrochloric acid reacting with sodium hydroxide. This is a neutralization reaction, and the result is that the temperature goes up. Now, because the temperature of the surroundings go up, again, this is an exothermic reaction. Energy is leaving the reaction, going into the surrounding calorimeter. In this case, the calorimeter is just this water that's already inside of the reaction. Now, whenever we say AQ, we mean dissolved in water. We're talking about this water here that is actually dissolved, or what is dissolving the powder of sodium hydroxide and hydrochloric acid in this case. And because the temperature is going up, that means that the speed of those water particles are getting faster. But we're not interested in how much these particles are increasing. They are negligible. It's just the water that was already there. So there's 2 cases here. This first one, where we take 2 solutions and we mix them. And then a second one, where we take a powder or a ribbon and we mix that with a solution, and then it's that water that raises. So again, here would have started slow at 17.5. We would have risen up to 31.5, and these water particles will now be going faster. Okay, so let's look at the math on these 2 things. We're just going to start off with Q today, and then we'll come back and do a bit more analysis. So Q equals mc delta T. Now for this reaction, in terms of what's raising in temperature, it is the water. Okay, it's almost always going to be the water unless they explicitly say something else. But if they say solution or calorimeter, they're talking about the water. Another interesting thing to know about water is that every 1 milliliter of water is equal to 1 gram of water. So, because we combine these two, 48.8 and 50.2, we have 99 milliliters of water. That is 99 grams of water. Next, you'll probably commit this number to memory, but here it is. The specific heat capacity of water is 4.19 joules per gram degree Celsius. So we're going to use that 4.19 joule per gram degrees Celsius. And then TF minus TI, which is 25.1 minus 19.3. Cancel, 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 cancel. And we have a little bit of math. 99 times 4.19 times by parentheses, 25.1 minus 19.3, close bracket, equals, I've got 2,406, and joules is my unit remaining. Okay, again, this could ask me to change it into kilojoules, just 2.41 kilojoules. Okay, looking at the next one, I've got this specific one because it forms a bit of an issue for some people, so let's chat about it. Once again, if you look here, I have two masses, but I'm not going to use the mass of the solid. I'm only going to use the mass of the volume and therefore the mass of the hydrochloric acid because this is AQ. This is what's dissolved in water. So when I'm looking at this temperature change, the calorimeter water, I'm looking at just the water from the hydrochloric acid. So after I put the solid in, it was 49.6 milliliters. It is still 49.6 milliliters. Here we go. Q equals M still to T. My mass is 49.6 grams because 1 milliliter is equal to 1 gram, so 49.6 grams. Same heat capacity for water. And finally, TF minus TI, 31.5 minus 17.5. Celsius cancel Celsius, grams cancel grams, and I'm left with my answer here. 49.6 times 4.19, bracket, 31.5 minus 17.5, close bracket. So this time, I've got 2,909.536. I'm going to round that to 2,910. And I'm really going to change that to 2.91 kilojoules. But here's all that stuff. So here's 209.536 joules. Round that to 2.9095 kilojoules. I usually like 3. So 2.91 kilojoules. Okay. All right, we'll talk about other things to do with this another time. Here's the last bit of information for today. Okay, I came across these two different ways that they could be giving you information in a test setting. They could give you a calorimeter to read, or sorry, a thermometer to read. So looking at this thermometer, 20 to 21, if you count out the intervals, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 0.0. So there's my value, right about there. We're always looking at the bottom of that meniscus. And what we get to is about 20.9. Now, because the increments are the tenths place, we're going to go one place further and predict what that position is. So in this case, I'm going to say that it's 20.90 because it's pretty well on exactly there. If I look up here, 73 to 74, it's still going up by tenths, so this is about 73.1. Now, if I wanted to say that that was a little bit below 73.1, all I have to do is pick a number between 73.0 and 73.1. It's very close to 73.1, but being just below, I'm just going to say 0.09. And then I'm going to use this later on to find my delta T to do my TF minus TI. Gave me my final reading, 73.09 degrees Celsius, minus my initial, 20.90 degrees Celsius. And I can find my temperature change, and I can use that for my calculation. The last way they could do this for you is by giving you a graph. They could say that the temperature was recorded every second for 5 seconds. You can see here it went from 25 to 36 in 3 seconds. This 3 doesn't matter. It's just that temperature change you're interested in. So really I'm looking from here to here. And I can see that my temperature change from 36 to 25 is a change of positive 11 degrees Celsius. Or I can do the math, TF minus TI, and my final is 36.0 degrees Celsius minus 25.0 degrees Celsius is 11.0 degrees Celsius. Okay, thanks a lot for tuning in. There's a bit of calorimetry. See you next time.